Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be going over the chemistry of vision. Again, we're going to be talking about multiple bonds in molecular orbital theory, but this time we're going to relate it to vision. We're going to start off with 1,3-butadiene, and then we'll go into vitamin A and retinal. So let's get into this. So there is something peculiar about organic molecules that have alternating double and single bonds in the molecule, right? This makes them how should I say? This makes them more stable than we would have expected, right? So let's talk a little bit about the structure and how this relates to molecular orbital theory, and then we'll talk a little bit about vision and color. So here we have butadiene, right? So it's CH2, CH, CH, CH2, and you'll notice there's a double bond and a single bond alternating, right? So we have double bond, single bond, double bond, single bond, or double bond, single bond, double bond in this case. So we'll point out right away that because of the double bonds here, you have sp2 hybridized carbons. So all the carbons in this molecule are sp2 hybridized, and that's typical of this alternating pattern of double and single bonds, right? So this is going to be important because if they're sp2 hybridized, that means that every carbon has an unhybridized p orbital, right? Because there's 3 p orbitals, you use 2 of them in the hybridization, so that leaves 1 unhybridized p orbital left over. So we have 4 unhybridized p orbitals, 1 on each of the carbons, okay? So then if we look at our sigma bond structure here, right? So we draw the sp2 hybridized. That means that all of the carbons are trigonal planar. So we have a trigonal planar structure for each of the carbons. And remember, when we set up our structure, we have to start with the total number of valence electrons. So since carbon is in group 4, it has 4 valence electrons. We have 4 carbons, so 4 times 4 is 16. So we should get 16 valence electrons from each from the carbons, all 4 carbons total. And then each hydrogen has 1 valence electron because hydrogen is in group 1. And we have 1, 2, 3, 4, 5, 6 hydrogens. So that's 6 valence electrons total. So if we add 6 to 16, that's going to give us 22 valence electrons total. But when we set up our sigma bonding structure here, you'll notice that we have electrons paired up in our sigma bond. So here we have all the sigma bonds, sigma bond between the sp hybridized carbons, right? So we have, again, sp2, I said sp, but sp2 hybridized. So this is sp2, sp2, and sp2. So when we fill in the orbitals with the electrons in the sigma bonds, right? So all of these are sigma bonds. Then we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we used 18 electrons here. Oops. So we have 18 electrons here that we used up. So if we subtract 18 from 22, we end up with 4 electrons left over. So that means we have 4 electrons that can then go into the 4 unhybridized p orbitals. So that means that we get to put 1 electron into each of the unhybridized p orbitals, and that's going to allow for pi bonding, right? So now we can go to our orbital energy level diagram, or molecular orbital energy level diagram, and remember the rule, or the principle, or rule if you want to use it, is that for every atomic orbital that is unhybridized that you use to create molecular orbitals, that's the same number of molecular orbitals that you get out. So when we saw from an earlier video with ozone, we had 3 unhybridized p orbitals. So you have those interact, you add those together, and you get out 3 pi orbital molecular orbitals, right? So in this case, since we have 4 unhybridized p orbitals, we got to combine those together, and we're going to get out 4 molecular orbitals, molecular pi orbitals. Okay, so we're ignoring all the sigma bonds and sigma molecular orbitals. We're only looking at the pi orbitals for this video. And so here are the different levels of the molecular orbitals. So remember, when we're talking about molecular orbital theory, we're talking about treating the electrons and the orbitals as wave functions. And just like any wave, the wave of an electrons can interact destructively or constructively. So if all of the orbitals, all of the p orbitals on the carbons are interacting constructively, you get overlap, electron density on the top and the bottom without any nodes, right? So this is the lowest energy possible, right? So 0 nodes on the bottom. This is all constructive interference, all interacting constructively, and so that lowers the energy a lot. And so this is the lowest energy molecular orbital, so we call that pi 1. Next, the other option is you could have 2 of them, interacting constructively, these acting constructively. Here we have constructive interference, so you get greater electron density on the top and the bottom. But here you have destructive interference, so you get this node in the middle. So there's 1 node here, so that's going to be higher in energy, less. So here you have anti-bonding interactions here. So you have negative, or so you have a node here. So 0 probability of finding electrons, 0 electron density. And then you go up here, you could have it interact or constructively in the middle, but here and here you have destructive interference, so you get 2 nodes. And then finally up here, there's all complete destructive interference. So therefore, we don't have any overlapping. You get 3 nodes. So this would be the exact opposite of this. So here you have the highest energy possible. And so here you have bonding. Here you have anti-bonding, and then here you're going to have somewhere in between like anti-bonding and non-bonding molecular orbitals. And so this is the energy level diagram, and then here are the molecular orbitals: pi 1, pi 2, pi 3 star, pi 4 star. And then we only have 4 electrons, so we're going to add the electrons to the molecular orbitals from the lowest energy to the highest, adding 2 electrons to each one, following the Pauli exclusion principle. We're going to start at lowest energy, following the Aufbau principle, right? And if we had equal energy orbitals, then we follow Hund's rule, but we don't have equal energy pi orbitals in this case. So when we fill in the 4 electrons, 2 of them are going to go here, and then the next 2 are going to go here, and then that's it. Now we can calculate the bond order, right? So remember, bond order is calculated according to molecular orbital theory by taking the number of bonding electrons, those are the electrons in the bonding molecular orbitals, subtract out the anti-bonding electrons, those are the electrons in the anti-bonding molecular orbitals, those are the ones with the star, and then you take that difference divided by 2. So here, I'll just do it here since I have room. So how many bonding electrons do we have? So those would be the molecular orbitals without the star. So I have 2 electrons here, 2 electrons here, that's 4 bonding electrons. How many anti-bonding electrons do we have? That would be those electrons that are in the star molecular orbitals, and you'll notice I have 0 in those, so that would be minus 0. And then I'm going to divide that by 2. 4 minus 0 is 4. So 4 divided by 2 is 2. So that tells me that I have 2 pi bonds. That is perfectly valid, and that makes sense because notice here that I have 2 double bonds. One is the sigma bond, right? So here I have sigma bond, and then I have a pi bond, right? But remember, in the Lewis dot structure here, or in this structural formula here for this organic molecule, these double bonds don't stay there because remember, according to molecular orbital theory, the molecular orbitals are sheared by all of the atoms in the molecule. And this is what makes a molecule like this more stable than you would expect because the electrons in the pi bonds are shared among all of the atoms. And this is due to resonance, right? So remember, resonance says that these electrons in the pi molecular orbitals are shared by all of the atoms in the molecule. And so because these double bonds can move, right? So these electrons are shared. So in this case, because you have the double bond, single bond, double bond, these double bonds are pretty close together. They're only separated by a single bond, right? So again, if you're drawing your resonance structures, right, this double bond could move here between these 2 carbons. So that indicates that the electrons in the molecular orbital diagram or in the molecular orbitals can be shared by these carbons here, and this double bond can move. So basically, because of the double bond, double bond alternating pattern, the electrons in the molecular orbitals are shared by all of the carbons, so that gives the whole molecule a higher stability than you would expect. So the bond order between all of these carbons is going to be between 1 and 2 because remember, these 2 pi orbitals, those pi orbitals are shared by all of the atoms. So we got to divide that up between among the bonds. So here we have 1, 2, 3 bonds. So if we were to take the 2 pi bonds, right, and I'll just do the math here. So I take the 2 pi bonds, divide that by 3 bonds because we have 1, 2, 3 bonds. That means that each of the sigma bonds here get an additional 2/3 of a pi bond, right? So this is going to be 1 bond from the sigma bond plus 2/3 of the pi bond here. So it's going to be 1 and 2/3 bond between these 2 carbons. And again, between these 2 carbons, it's going to be 1 sigma bond and 2/3 of a pi bond. And then here we're going to have 1 sigma bond plus 2/3 of a pi bond. So all of these are going to be equal in the fact that their bond order is going to be 1 and 2/3 bonds. 1 sigma bond and 2/3 of a pi bond. So therefore, this is going to be more stable than you would expect. Okay, so I hope that's clear. So now let's talk a little bit about vision. So the idea that I want you to walk away with regard to vision is that remember that the more atomic orbitals that you add together, that you combine, the more molecular orbitals that come out of that. And the more molecular orbitals that come out of that, the closer the energy levels, the closer they are in energy as you multiply the number of molecular orbitals. Same thing happens with atomic orbitals. The higher you go up in energy, the more atomic orbitals you have, the closer in energy they're going to be. It's similar with molecular orbitals as well. So In this chain, we have 4 molecular orbitals. And so those 4 molecular orbitals are going to be closer in energy than if you had only two carbons together. But if you only have two carbons together, you don't have the you don't have the double and single bond alternating pattern. Okay, or if you have three, you could get that. You could have a single and a double here. So if you have three, you could get 3 orbitals or 3 molecular orbitals, and those would be farther apart in energy because this has 4 carbons with a double single bond alternating pattern. Then you're going to have 4 unhybridized p orbitals that are going to form the 4 molecular orbitals. Those 4 molecular orbitals are going to be closer in energy. If I was to have a 5 carbon chain with a double single bond alternating pattern, that would make 5 unhybridized p orbitals. So I would get 5 molecular orbitals. And so those 5 molecular orbitals would be close in energy. So the more atomic orbitals that I'm adding together to get the molecular orbitals and producing more molecular orbitals, those molecular orbitals are going to be closer and closer in energy. Why is that important? That is important because the closer in energy they are, then the easier it is for electrons to jump up to a higher energy, meaning that it doesn't take as much energy to excite those electrons to the next highest energy level. And so that brings me to this idea of HOMO versus LUMO, right? So you may or may not have heard of these terms. HOMO just means highest occupied molecular orbital, right? So what does this mean? This is the highest energy molecular orbital that has electrons in them, right? So I have electrons in this one, and I have electrons in this one, but then I don't have electrons in this one. So we call this the HOMO, the highest occupied molecular orbital. Occupied by what? Electrons. And then right above that one is what we call the LUMO. And as you could probably guess, LUMO is the lowest unoccupied molecular orbital. Unoccupied because it doesn't have any electrons in it, right? So this one doesn't have electrons in it, but this is higher energy. So we're looking at the lowest unoccupied molecular orbital. Why the highest and lowest? Because those are going to be right next to each other. So right above the highest occupied molecular orbital is going to be the LUMO, which is the lowest unoccupied molecular orbital. Why is that important? As I just said, the more molecular orbitals you have, the closer in energy they're going to be. So that means your HOMO and your LUMO are going to be closer and closer in energy. And the closer in energy they are, the less energy that's needed in order to excite the electron in the HOMO up to the LUMO. And if you get low enough energies, if you get close enough, then if the energy is small enough, the necessary energy needed to excite the electron to the next higher LUMO, then that energy range could be within the visible energy spectrum, the visible light spectrum, right? So then things can have color. Things will look colored to us, right? So if I absorb a small enough energy that's within the range of, say, the purple color, right? If I am able to absorb light in the range of the purple color, then that's going to make the substance look yellow because that's the opposite complementary color, right? So if I'm absorbing purple, then what's being reflected to my eyes is going to be the opposite complementary color, and so that's going to look yellow to me, right? So that's where our vision of color is coming from, right? So I'll talk more about this. So let's get into retinal and vitamin A, and I'll talk a little bit more how the increasing of molecular orbitals causes the energy difference to be closer. So stay tuned. Okay, so now I have here a diagram of what is going on when you have more atomic orbitals being added or combined together to form molecular orbitals. So you can see here on the bottom, these are the number of atomic orbitals that are available to add together. So these are the non-sigma orbitals, if you will. So you can see that as the number of atomic orbitals that are available for combining increases, then of course the number of molecular orbitals that are produced from that combination also increases. And so you can see here, if you have one atomic orbital, then you've only got one molecular orbital. So these are just to kind of explain and clarify what this is. If I put lines in between here, right? So here, this is one molecular orbital diagram. This is the molecular energy level diagram. So I'm going to separate these. So hopefully this will make it clearer. Okay, so then here, this is the molecular orbital energy diagram for if you only have one atomic orbital. So if you have one atomic orbital, then you only have one molecular orbital. If you have two atomic orbitals that are being added or combined together, then that gives rise to two molecular orbitals. And if you have three atomic orbitals that can be combined, then you're going to get three molecular orbitals in the energy level diagram, and so on. So four molecular orbitals gives you four atomic orbitals gives you four molecular orbitals, and five atomic orbitals gives you five molecular orbitals. And the important thing that I want to point out here again is that the more atomic orbitals that you have that are combined together, giving rise to a larger number of molecular orbitals, and the more molecular orbitals that are combined, the closer in energy those molecular orbitals are. So you can see that the difference in energy between these two molecular orbitals is going to be larger than the difference in energy of these three, which is larger than the energy of between these four, and which is larger between the energy of these five. So again, why is this important? The importance of this is that the closer the energy, the closer in energy of the molecular orbitals, then the less energy required to get an electron to be excited from the HOMO to the LUMO, the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And again, the more carbons you have, right? This is kind of, we're talking about vision here, right? And we saw that the delocalization of the electrons is related to how close that those double bonds are and the resonance structure, right? So the more p orbitals you have that are unhybridized, that are available for molecular orbital, combination, right, to form those molecular orbitals, uh, then the closer energy those molecular orbitals are going to be, right? So that's the importance here. So if you can get the energy levels close enough, then you don't need as much energy to excite those electrons, right? So that means that if you have a large enough, system, then you can have more molecular orbitals that are close enough such that the energy of the photon falls within the visible spectrum range, right? And so then you can have the electrons absorb energy from different wavelengths of light that match with different colors like purple and yellow and orange and green and blue, right? So that's the importance of this. So that brings me to vitamin A and retinal. So you can see here that this is the structure of the molecule known as vitamin A. Vitamin A turns out to be a yellow color. And you can see here that we have this long double bond, alternating pattern of double bond and single bond. So we have uh, 10 carbons here. And so you have a single bond, double bond, single bond, double bond. So you have like 5 alternating double bond and single bonds here. And so because you have this alternating pattern, all of these carbons here are sp2 hybridized, meaning that they all have one unhybridized p orbital. So if you have this p orbital here, so this carbon, 1, 2, 3, 4, 5, 6, 7, 8, and maybe 9 if we include that one. So 9 carbons, each having an unhybridized p orbital. Well, not that one. That one's that's sp3 hybridized. So just the 8 carbons here, all of which are sp2 hybridized, which means that they all have an unhybridized p orbital. So you have 8 unhybridized p orbitals that can then combine to give you 8 molecular orbitals. Well, the energy difference between those molecular orbitals is going to be quite small enough that it can absorb energy in the visible light spectrum. So in this case, vitamin A is yellow because it's able to absorb energy from the purple or violet energy range. So it's absorbing the energy from the violet spectrum, and therefore the yellow light, the light in that range, is being reflected. That's what your eyes receive, and therefore you see or perceive the color yellow when you see vitamin A, right? So how does this also explain vision in our eye? Like, so our eyes, we're able to see. Well, how is that explained? That brings me to the structure called this molecule called retinal. Now, retinal is a molecule that binds to a protein in your rod cells. So if you remember, in your eyes, you have rod cells in your eyes. Those rod cells have a part that's made up of discs of membranes. In the discs of the membranes, in the membrane of those discs, you have a protein called opsin. Opsin, it binds to a molecule called retinal. When retinal and opsin are together, that forms a complex called rhodopsin, right? So you may have heard of rhodopsin if you've taken an organic chemistry class or a biochemistry class, right? That talked about this. This probably came up in your class. So in rhodopsin, you have opsin, the protein opsin, that is a membrane, a transmembrane protein. It binds with retinal. Now, it binds nicely with the cis structure. Now, what we mean by cis and trans is basically cis refers to the large, bulky parts of your molecule on the double bond are on the opposite side. And if it's cis, they're on the same side. So trans means the bulky parts are opposite sides of each other. The cis means that the bulky parts are same side of the double bond. So for example, here, if we look at this double bond here, if we look at this part here, that bulky part is on this side of the double bond. And then this bulky part, right, if we're just focused on this double bond here, then this part here is on the opposite side of this double bond. So you could see here that that would be trans. So this bulky part on this side, this bulky part on this side. Now, if we look at this double bond here, do the same thing, right? So this bulky part here is on this side of this double bond. And then this bulky part is again on the opposite side of this double bond. And you can look at that for each double bond, and you'll see that every double bond has a trans structure, right? So this is called the trans isomer of retinal. Now, you could see here that for the double bonds, we have trans and trans, but then this double bond here is the key double bond. What happens here is when light hits this double bond, right, it can absorb, and this we're talking about light in the visible spectrum. So light in the visible spectrum can break this double bond, right, because of the closeness of the uh, molecular orbitals. So this bond then can become a single bond relatively for a very short period of time, long enough to spin or rotate 180 degrees, and then the double bond will form again. And then what you'll get is the trans form, right? So this is what it looks like in the cis form. And so it's cis. Why is it cis? Because now if we focus on this double bond, we can see that this bulky part of the double bond is on this side, and then this bulky part here is also on the same side. They're both on the same side of this double bond, so that's cis. Cis means on the same side. Trans means on opposite sides. So this is what we call the cis isomer of retinal. This is what we call the trans isomer of retinal. So what does that have to do with vision? Right, as I said with the rhodopsin complex, right? So this shape here, the cis isomer of retinal, fits nicely into the protein opsin, right? However, when this absorbs light, so light is absorbed, that double bond breaks, becomes a single bond momentarily, long enough for the rotation around the single bond to occur, and then it will reform the double bond. But when it reforms the double bond here, you'll see that now it's trans. So this is a straight molecule. This is a bent molecule. The bent molecule fits nicely into the pocket of the opsin protein, right? The active site, we call that the active site. So this will fit nicely into that pocket of the protein. This will not. But the protein will try to shift or change shape in order to accommodate this. What happens when the protein starts to shift or change shape? Well, that's going to, remember, this protein opsin is, or rhodopsin, if we're considering retinal plus opsin, the rhodopsin protein, it's a transmember protein. So if it changes shape, then it's going to cause the membrane to change shape and kind of straighten out. Well, this is not happening just to one rhodopsin protein in your cone receptors. I'm sorry, your rod receptors, right? The rod receptors, this has many of these rhodopsin proteins, transmember proteins. So this is happening to a whole bunch of them. So if this is happening to a whole bunch of them, it's going to cause the membrane in the disc to kind of straighten out. That's going to cause the structure to change, and then it's going to cause this change in the structure to kind of reverberate or kind of translate throughout the whole rod cell, the whole rod cone, or I'm sorry, I keep getting mixed up. The rod in your eyes, and then so that change is gonna translate into a signal that's passed on to your brain, and then your brain will interpret that as color. And so then you're able to perceive whatever color it is. And then what happens is, again, the trans will go back to the cis through enzyme action. I won't get into that, but this is pretty much what's happening in your eyes. Your rod cells are responsible for night vision, right? So if there's a problem with retinal, then your night vision, your ability to see in dim light is going to be hindered. So you might have heard of people who grow older, they lose their kind of their night vision, so they can't really drive at night, right? That has something to do, or it could possibly have something to do with retinal. And this is why vitamin A is really important for your night vision, your retinal. So you can see here that vitamin A is almost exactly the same as retinal. The only difference between retinal and vitamin A is here you have a hydroxide a group, OH, and then here you have an aldehyde group, which is why you have the Al ending. Anytime you have an Al ending for an organic molecule, that indicates you have an aldehyde group in your molecule. But this is a hydroxide group. That is the only difference. So you can see that if you have a vitamin A deficiency, that's going to lead to problems with your eyesight, especially your ability to see in dim light, because of course that's going to affect the retinal, right? No vitamin A, you're going to have a depletion in retinal and you're not going to be able to see at night or in dim light. So this is very important. Now, philosophical question. This raises questions. Now, so does if this is where our ability to see colors come from, then the question might rise: is where is color then? Is color out in the object itself, or is it in my head? Is it in my brain? Is it just perceived? Or is it out there? That's a philosophical question that you can think about, and maybe I'll do a video on that. But that's it for this video. If you enjoyed this video, if you like this video, if you learned anything from this video, then by all means like the video, share the video, hit that like button somewhere around here. Also, subscribe to my channel, hit that notification bell. Do me a favor. When you hit the notification bell, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic that you would like me to cover, write that down below, and I'd be happy to do that for you. Thanks for joining me, and have a great day.